Gas is a unit of measurement in Ethereum network, where gas unit is represented in GWei, means gigawei, which is a denomination of Ether coin, where 1 GWei is equal to 0 dot followed by 8 zeros and 1 ethers. Gas on Ethereum network acts as same as a fuel for a car. Without the fuel, the machine won't run. So, to make changes to the state of the Ethereum network, the person who is sending the transaction is required to send additional ethers along with the transaction to be used as gas. The additional ethers that is sent is given as reward to the validator for including the transaction in a newly created block. For example, if Sarah is sending 1 ethers to Alex, she has to send 1.00252 ethers, and 1 ethers is sent to Alex's wallet address and 0.00252 ethers is sent to the validator who validates the transaction and includes in the new block. Before we look at how gas price for a transaction is calculated, we need to know about opcodes. Whenever a smart contract is compiled to bytecode before deployment, it is further compiled down to opcodes. These are simple operations that can run directly on the Ethereum virtual machine. These opcodes include basic operations like add, multiply, division, subtraction, etc. Each opcode has a fixed gas cost. The gas cost of a specific function within the smart contract is the sum of the gas cost of all the opcodes. Therefore, more complex transactions which require more opcodes to execute end up using more gas than simpler transactions like transferring ETH from one account to another. A list of all the available opcodes and the gas consumed by EVM to run the opcode is listed in this GitHub page. On August of 2021, the London upgrade happened, which changed the way gas is calculated. We will look at two parts, pre-London upgrade and post-London upgrade. Prior to the London upgrade, gas is calculated based on the below formula. Gas fees is equal to gas spent multiplied by gas price, where gas spent is the amount of gas that the EVM needs to process the transaction, and gas price is the amount of gas you are willing to pay per unit of execution. The cheapest transaction in terms of amount of gas required to execute is the transfer of Ether from one account to another. This transaction costs 21,000 gas units. When Sarah sends 1 ethers to Alex, assuming 200 GWei as gas price per unit of execution, gas fees would be 21,000 multiplied by 200 GWei, which is equal to 4.2 million GWei, or 0.0042 ethers. You might be wondering how the gas price is set to 200 GWei. This depends totally upon the user. Whatever the user chooses to pay shall be set as gas price. But the higher the gas price, the higher the priority of the transaction to process. Note, if you send less gas fee than the gas required by the EVM, your transaction will revert and the gas fee you sent will be gone. Gas limits. It can be hard to predict the gas fee by the user, as gas price might vary based on a lot of factors. But you can set a maximum amount of gas you are willing to pay for the transaction. The EVM will use only the necessary amount of gas and return the rest of the gas fee back to your wallet. Block gas limits. In addition to the user-specified gas limits per transaction, the Ethereum network also imposes a limit on the maximum amount of gas units allowed in a single block. This is done to ensure that each block stays within the allowable range of computational cost, since more complex transactions take longer to execute. This makes sure that nodes don't start falling out of sync with the rest of the network due to increased computational complexity. Next, we'll look at post-London upgrade. On August 5th, 2021, the London upgrade was implemented on the Ethereum network. This upgrade primarily introduced two benefits to gas fee: better gas fees estimations and quicker transaction inclusion. The formula to calculate the gas fee was slightly modified to gas spent multiplied by base fees plus priority fee, where base fee was the minimum price per unit of gas for getting your transaction included within this block. This was calculated natively by the network based on the demand for block space. These base fees would go on to be burnt by the Ethereum network, therefore forever getting rid of the ETH to offset issuance. The priority fees is just the tip that is given by the user to validator. As the base fees got burnt, the tip was there to compensate validators for executing and propagating user transactions. Going back to the earlier example, if Sarah had to pay Alex 1 ETH, the gas cost in units is 21,000 gas. Suppose the base fees is 100 GUI and Sarah decides to include a tip of 10 GUI, so the total gas fees would be 21,000 multiplied by 100 GUI plus 10 GUI, which is 2,310,000 GUI, or 0.00231 ethers. Variable block sizes. As mentioned earlier, prior to the London upgrade, the block gas limit was constant for all blocks. Each block had the maximum capacity of 15 million gas. In times of high demand, this resulted in bad user experience, as blocks were operating at full capacity and users had to wait for the demand to reduce to get included in the block. The upgrade introduced variable size blocks to Ethereum. Each block now has a target gas limit of 15 million gas, but the size can get increased or decreased along with network demand up until a maximum of 30 million gas. If the block gas is greater than the 15 million target, the base fees for the next block is increased. Similarly, if the block gas is smaller than the 15 million target, the base fees for the next block is decreased. The base fees is increased by a maximum of 12.5% per block if the target 15 million gas is exceeded. This change led external applications to accurately determine the base fee for a transaction that is about to happen, which is very helpful for wallets and other applications. Gas fees help keep the Ethereum network secure, by requiring a fee for every computation executed on the network. Bad actors are prevented from spamming the network.